Welcome to Market Matters, our markets podcast on making sense, the hub for JP Morgan Corporate and Investment Bank podcasts. In each episode of Market Matters, we discuss the latest news and trends shaping markets today.
Hi, I'm Eloise Goulder, head of the Data Assets and Alpha Group here at JP Morgan. And today I'm really delighted to be sitting here in New York in person with Peng Cheng, who's head of big data and AI strategies in our global research team, and Emma Wu, who is a member of Peng's team and who has done a lot of work on AI strategies. And we're now opening up part 2 of our discussion, where we're really going through demystifying AI in the financial domain. So on to our 4th major set of machine learning models, and I think that was neural networks. Emma, let's start with you again on the definition. So how would you define neural nets?
So neural nets have become a cornerstone in machine learning, especially in the recent years. There are some terms that specifically used here, such as node or neuron, layers, activation functions. So before going into the definition of neural net, we can define those specific terms first. A node or neuron represents a unit that has one or more weighted input connections, or a function that combines the inputs in some way, or an output connection. And nodes are then organized into the layers. A layer could be input layer, hidden layer, and output layer. Activation function are like filters that decide how much information a node should pass on, which can be set from linear to nonlinear, simple to complex. I find the best way to understand neural net for someone with an economics or finance background is by making the connection with regression models. A one-node, one-layer neural net with a linear activation function is just a linear regression with one variable. And if you want to model something nonlinear, say a probability bounded between 0 to 1, we can change the activation function to a sigmoid function. Now the neural net becomes a nonlinear regression. And if we have multiple input variables, we increase the number of input nodes. Now the neural net is a nonlinear multivariate regression. If we want to run multiple regressions simultaneously, then combine their output, like an ensemble model that we discussed just now, we can add a so-called hidden layer with multiple nodes, and now this becomes a deep neural network. So as you can see, the structure of neural network can be highly flexible, and there are many architectures out there to handle different problems.
That's such a helpful way of explaining neural nets. Thank you, Emma, because obviously these models can become highly complex and highly computationally intensive, but your point that actually a one-node neural net with a linear activation function is just simply linear regression, where we started this conversation, I think that's really helpful to understand. So Emma, within this wider neural nets methodology, are there different categories that we need to be aware of?
Yeah, so as you said, there are a wide range of neural nets here, but today we focus on recurrent neural net, RNN, long short-term memory, or LSTM, and attention. As you know, some data series have memories, and meaning the previous output help predict the next output. It's similar to the concept of an AR1 model in linear regression. However, if the series has a very, very long memory, adding all the lagged inputs oftentimes creates a weird structure. Recurrent neural net manages to accomplish this by not carrying all lagged values, and instead it specifies a forget rate, and the previous information will decay as a function of this forget rate. However, as information needs to be propagated over many timestamps in RNN, it oftentimes has difficulty in capturing long-term dependencies. And this is the so-called vanishing gradient problem, which can come across during the training period when the gradient of the loss function with respect to the parameters become extremely small as they move backwards through time. And this makes it challenging for the model to process the distant past information. Further variations of RNN, such as LSTM, have improved this problem but not completely addressed it. An attention mechanism is developed to address this issue by enabling the neural net to assign different weights to different parts of the inputs, instead of following a function of a decay rate. So in our study, we actually have multiple publications on comparing those models and their different scenarios.
That's brilliant. Thank you, Emma. So you described those 3 different types of neural net methodologies, the RNN, the LSTM, and the attention. And as far as I can work out, these all offer various solutions to the problem of memory retention, which actually reminds me of the conversation that Peng, you and I had back in the podcast recording in September when we were talking about the man versus the machine. And we were talking about the fact that the man, the human, in many cases has a very good long-term memory and or a very good understanding of economic history, financial history, that sort of thing. Whereas some machine learning models can fall short in that sense because they don't necessarily have that knowledge of history. And it's often very computationally intensive to remember that long-term history. And I remember you talking about the creation of the attention model. I think it was from Google back in 2017. And the fact that that was attempting to overcome some of these challenges.
That's right. So they published the paper titled Attention is All You Need, which is the attention model we discussed here. And as you mentioned, it does a very good job in addressing the problem of memory retention. And it is the underlying architecture for a lot of the large language models we see today. And we can get into that a little bit later. But just in terms of the attention model itself, we can use it to model time series very effectively. And if you think about which time series in finance has the strongest memory, I would probably argue it is volatility, because I think we can all agree that days of high volatility tends to lead to more days of high volatility and vice versa for days of low volatility. So when using the attention model, we find that it is very effective in modeling this kind of volatility behavior, not only in short-term memory, but also in long-term memory. And that is pretty much the kind of behavior we observed in the volatility trading market. And we have shown that by using attention model, we're able to produce much stronger profit in trading volatility than using classical econometric models. Of course, there are drawbacks that come with it as well. And as we've emphasized along the way, it's the heavy computational and data requirements. And I think that the previous models we discussed, they can all probably be run on local machines in a productionized environment. But with attention, generally speaking, you need GPUs and cloud computing to run. So, you would need specialized knowledge to handle such heavy compute models as well as large data sets.
Yes, that drawback absolutely makes sense. But we all know that compute availability is improving over time. I mean, do you think that drawback will become less and less of an issue in terms of practical uses of the attention model?
Yeah, I think so. I think even though it is heavy on the compute, I think progress has been made in both increase the computational availability. GPUs, for example, at the same time, models are also being made more efficient so that it takes up less compute power. So I don't see it as a huge obstacle to implementation.
Thank you. And wow, what a lot of keywords there. So you've gone through neural networks, RNN, the forget rate, the vanishing gradient problem, the LSTM, the attention, the node, the layer, the activation function, the hidden layer. Huge amount. And Peng, I think you provided a great segue there into the machine learning models category number 5, the large language models, because you said just then that attention models are very much behind them. Peng, before we go into them, can you just explain if LLMs are a totally distinct area of machine learning or if they're actually quite related?
Yeah, actually, I think so far everything we've discussed seems so different from ChatGPT, right? I mean, how are they related? Actually, I would say that they're very closely related because what we're doing so far is we're using past numerical values to predict future numerical values. But what ChatGPT does is that it uses past text to predict future text. So how it does so is by using an architecture called transformer. And a transformer is made up of 3 parts. The first part is called the encoder. The second part is the attention model, as we just discussed. And the third part is the decoder. So what do these 3 parts do? Well, actually, transformers, although they're complicated, a large part of their effort is focused on one thing, which is translating between words and numbers. Computers obviously cannot read words. They can only read numbers. So what encoder does is that it takes words and translate them into numbers. Exactly how it does so, is very complicated, but I can also give you a simple version. I can randomly or arbitrarily assign values to words. You can imagine, okay, we're sitting in a cinema. The word apple is assigned seat 3A, for example, right? And that 3A is completely arbitrarily assigned. But I need to give it a lot of thought in assigning which words should be sitting next to the word apple. If I were to assign a word like orange next to apple, right? Or should I assign a word like iPhone next to Apple? If I assign words like iPhone and Samsung next to Apple, then this encoding becomes finance specific, right? Otherwise, if I assign words like banana and orange next to Apple, this is a more general purpose encoding. And over there, as you can see, a lot of decisions have to be made and a lot of differentiations will result because of that. But once we've done this encoding, we've translated words into numbers, then we feed it, just like before, into an attention mechanism. And what this attention mechanism will do is look at past words and predict what the next words are likely to be. If it reads inputs such as how are, then it will predict the next word to come out will be you. But of course, these are all, again, in numerical values. What it needs is a decoder to translate these numbers into words again. So as you can see, the structure is an encoder translating words into numbers, attention, use these numbers to predict the next number, decoder, translate numbers back to words. So that's how essentially a large language model works.
That's so helpful, the way you describe the transformer model, encoder, attention, decoder. Thank you for that. So Peng, how do we go from this transformer definition through to large language models?
Yeah, large language models are collections of transformers, and it results in very, very large model, as its name suggests.
Yeah.
So let's say ChatGPT, GPT-3, for example, has 175 billion parameters. That's obviously a big number, but there are even models that are bigger, and that's why they're known as large language models. And sometimes I get a question, again, a lot of times from people with a statistical background, models with such a large number of parameters, how do they avoid overfitting? Well, this goes back to, again, a difference between machine learning and statistics philosophically. By using numerical methods like cross-validation, dropouts in neural network, we are confident to prevent overfitting even with such large number of parameters. And I think when you look at the results produced by ChatGPT, you can agree with us. And we can also talk a little bit about what generative AI is. And this is, again, another buzzword alongside large language models. For us, I think we would define generative AI as AI models that can generate predictions not only one step ahead, but multiple steps ahead. So this means the model not only has to predict what the Y variable is, but also all the associated X variables. I think in the media, you oftentimes see generative AI in the form of text or images, but actually in finance, we can use generative models to create synthetic financial data, and that has a lot of use cases. So maybe lastly, how are these transformer models turned into chatbots like ChatGPT? So what it does is it takes words as inputs, spit out the next word, and then based on its previous prediction, it feeds into itself again and spit out the next words, and so on and so forth. And this process keeps iterating. And that's how it produces a conversation like you see on ChatGPT.
It's absolutely incredible. And there, I guess you've given us our final keywords to be taking in today. So transformer, encoder, attention, decoder, GPT-3, generative AI, synthetic data, and chatbots. So can we talk about use cases for this in our domain, in the finance domain? And Emma, do you want to take this? What key use cases would you talk to using this technology?
Yeah, so one use case is we created a platform called Smart Bus. It's our proprietary large language model trained on JP Morgan proprietary data. So basically, the underlying methodology is we use over thousands of themed terms or financial phrases to scan millions and various texts, such as current news, transcript, JP Morgan analyst research, and so on, and flag any mention as well as the context surrounding the term. And then we assess if a mention was in a good or bad context so that we assign a sentiment score that positively or negatively associated with a company. And this scores ranges from -1 to 1, and we can aggregate to any level in the hierarchy, such as go to the sector level or country level. So in short, it translates the unstructured data to a weighted exposure factor or a score that measure positive or negative sentiment across different granularities. Some typical usages using this model, for example, at company level, it helps measure a theme sentiment towards individual stocks so that investors will have a better insights to manage the exposures.
Brilliant. Well, I know that that is a really powerful use case that you have up and running. And actually, Peng, you told me lots about it in our last podcast discussion back in September. And I think that you showcased the conclusions of lots of your Smart Buzz analysis on your website. Is that right?
Yeah, so Smart Buzz is now on our major website at JP Morgan Market. It's called Investable AI. So people can free to check what's the latest sentiment score in different categories, as well as time series of sentiment score, like how it changes back to 3 years.
Wonderful. Well, what a huge amount of information I've just taken in and our listeners will have just taken in. And how incredible that over the course of this conversation, we've gone through, I think, more than 40 different keywords or machine learning terminologies and explained them. So I guess an important area we should cover before we close is challenges. I know you've already articulated the pros and cons of each of the various models, and generally it helped me understand why, in many cases, if you have the processing power, it does make sense to work up the complexity ladder. But Peng, how do you think about challenges more generally with all of these approaches? Is there anything you'd observe?
I think as complexity increases, we obviously need larger amount of data, but at the same time, the quality of data has to increase as well. So in other words, more complex models is not good at treating low quality data, but instead it should be provided with higher quality data. And handling large quantity of data also requires more thoughtful treatment as well. On top of that, we need efficient design of algorithms during the research and development as well as the production phase. So this is very different from a simple model where we can just code it in one line. So yeah, it does require a lot more specialized knowledge when handling both large amounts of data as well as algorithm design.
Fantastic. So before we wrap up, I was going to ask, what are your favorite models? So can we turn to those? And I'm not sure if you'll both agree on this or if you'll have different answers. But Peng, shall we start with you?
Yeah, I think every model has its strengths and weaknesses, as we discussed. But I just want to make one point, which is we don't believe that large language models is this omnipotent thing that will take over everything. In fact, we believe specialized models, whether it's classical or deep learning model, can outperform large language models on domain-specific tasks, especially when trained on domain-specific data. Obviously, that does not come for free. With LLMs, you can ask a question and get an answer quick and dirty. But with specific models, it requires long development time and a lot of effort. But, we think a lot of times it warrants this additional effort. And if I have to pick a model that we're focusing on, I would say it's probably transformers. We see it having enormous potential for time series modeling beyond its use in natural language processing. And we have a few projects underway with using transformers.
Brilliant. And Emma, do you have any additional thoughts on this?
I agree with Peng that if I have to choose a model in our current study, I'll choose attention. It's not because, as he said, the large language model is always the best to be used, but it's really under current scenarios in the volatility forecasting study that we work on. Attention model outperform other models such as SVM and simple linear regression? Well, I think at the end of the day, there's always a trade-off between the computational power and accuracy. So it's always a good practice to apply different models, do hyperparameter tuning, and then decide which is the best one to use. Sometimes linear regression model also outperforms, and the simpler the better.
Excellent. So another topic that comes up a lot in my conversations around machine learning is whether or not we should be hypothesis driven. Because I think in the old world of statistics and econometrics, but pre-machine learning really taking off, there was definitely a philosophy that you wanted to minimize the number of input variables in a model, and you really wanted to minimize overfitting. And therefore, it was critical that the user has a prior hypothesis that they then go on to test, versus potentially in the machine learning culture that you refer to, there's less of a respect perhaps for the domain knowledge and the hypothesis testing. And because there are so many ways that one can overcome overfitting, and therefore more of an acceptance of multiple variables and model complexity. Peng, how do you think about that?
Yeah, I think parsimony, as we discussed, is definitely something we can probably be a little bit less obsessed. But the data availability in finance and computational power availability in general is not so great yet that we can completely discard prior belief. So I think domain knowledge is still very, very important.
Yeah. And Emma, to the extent that our listeners want to learn more about all of the terms that we've discussed today, are there any resources that you would really point to or recommend?
Yeah, so one useful website is Machine Learning Glossary by Google developers. So this glossary page defines the general machine learning and AI terms, plus some terms specific to TensorFlow. I frequently look it up, and I think it's very useful, especially when you are unsure about the definition of a term. Other than that, I would highly recommend a hands-on website called Kaggle. Users of it can access a diverse collection of datasets from different industries. It also provides a feature called kernels, where users can share and explore code notebooks so that you can study others' implementations and potentially exploring different approaches or methodologies to solve the same problem. It often hosts a wide range of real-world projects and competitions so that users can solve practical problems using AI and machine learning methodology. I find it's particularly useful because the community and discussion board there creates a supportive environment for learning and knowledge exchange.
That's brilliant. And Peng, is there anything you'd add to that list?
I like to read a lot of academic research papers, and I find that generally speaking, it's more productive to read papers written by finance academics and professionals using machine learning techniques rather than reading papers written by computer science academics and professionals. So the two websites I like to look up are SSRN, Social Science Research Network, and Archive, ARXIV. They both contain a lot of useful academic papers in quantitative finance in general and machine learning in particular.
Excellent. Well, Peng, Emma, this has been a really fascinating conversation. Thank you so much for taking the time to go through all of these 5 broad machine learning models in such depth. I guess what's really stood out to me is a few things, really. So first of all, the link between basic statistics and machine learning, and the idea that machine learning is really, in a way, just the processing using machines of statistics, and that given processing power has increased enormously over the years, the point is that we can now leverage these much more complex statistical methods via machine learning in a way that we just couldn't practicably do previously. So I think that's one fascinating takeaway for me. The second one is that several terminologies that are used in machine learning actually have a different name in statistics, but they ultimately mean the same thing. So the one that really stood out to me is the word feature. We always hear about features in machine learning, but really that just means independent variable or X variable, which might end up being explanatory variable. And then finally, one thing that's really stood out to me today is your explanations on why complex models are often superior to the more simple ones. To quote you, Peng, the world isn't linear. You said that during our discussion in September, and we need to capture non-linear relationships. And similarly, the world isn't discrete, is it? And hence there's benefits to support vector regression over random forest, as you just articulated. And hence, no surprise, I think, that you've tended to find better predictive models and greater alpha potential using the non-linear and the more complex models. And this type of alpha is a term that you call computational alpha, because without the processing power of the machines, you probably just couldn't identify this sort of complex relationship. So thank you very much for defining all of those keywords around the machine learning space, and in particular, taking it back to our domain, the finance domain, the quant research domain, the alpha generating domain. I think that's what's so powerful. And it's so brilliant to hear about all your work and research and data that you're working on to leverage these methods. So I really look forward to seeing how you drive these forwards next year. So thank you very much.
Yeah, thank you, Eloise, for having us.
Yeah, thank you, Eloise. Definitely great to be here.
Wonderful. Thank you also to our listeners for tuning in to this bi-weekly podcast from our group. If you'd like to learn more about Peng and Emma's work, then please do head to their JP Morgan Markets page. If you head to jpmm.com, then you can search Investable AI and you'll find all of their work and resources there. Otherwise, if you'd like to get in touch, then do head to our website at jpmorgan.com/market-data-intelligence. And there you can always send us a message. And with that, we'll close. Thank you.
Thanks for listening to Market Matters. If you've enjoyed this conversation, we hope you'll review, rate, and subscribe to JP Morgan's Making Sense to stay on top of the latest industry news and trends. Available on Apple Podcasts, Spotify, Google Podcasts, and YouTube. The views expressed in this podcast may not necessarily reflect the views of JP Morgan Chase & Co. and its affiliates, together JP Morgan, and do not constitute research or recommendation advice or an offer or a solicitation to buy or sell any security or financial instrument. They are not issued by JP Morgan's research department, but are a solicitation under CFTC Rule 1.71. Reference products and services in this podcast may not be suitable for you and may not be available in all jurisdictions. JP Morgan may make markets and trade as principal in securities and other asset classes and financial products that may have been discussed. The FICC market structure publications, or to one, newsletters, mentioned in this podcast are available for JP Morgan clients. Please contact your JP Morgan sales representative should you wish to receive these. For additional disclaimers and regulatory disclosures, please visit www.jpmorgan.com/disclosures. Copyright 2023 JP Morgan Chase & Company, all rights reserved.